Dr. Apostolos, Kantzas from the University of Calgary, talking about nanotechnology in geothermal and reservoir applications. Please.
Hello? There we are. I would say hold your applause until after the presentation. You may regret it, but thank you anyway. So I was told to prepare a presentation on geothermal and reservoir applications. I added the plus. I have some extra goodies there if we have time. Can I have the screens? So this is the group, and there's a lot of people. They have to do a lot of things. These are the ones that are doing all the work. Essentially, the program is two different sets of projects. The first project is dealing with the fundamentals of unconventional resources, more related to heavy oil and tight oil. And then the other project group is called Energy Harvesting Processes, which deals with geothermal and energy harvesting from different sources. If we look at the group as a whole, we have split it based on the physics that they are dealing with. So we have the group in electroacoustics, and this deals with using ultrasonic and electromagnetic reactors for us to do various types of things, including sensors for multi-phase flow measurement, as well as upgrading of heavy oil and bitumen. We have the digital lab that is dedicated to pore level modeling. We do not believe that anything can be properly understood unless we actually tackle it at the pore scale. We have the heat transfer group, which includes the geothermal, and it includes heat transfer modeling of thermal processes. We have the enhanced oil recovery group that deals mostly with heavy oil and tight oil EOR. And finally, the nanotechnology group that deals with design and implementation of different nanoparticles for different applications, including geothermal. So the first project that I'm going to present to you today has to deal with how can we use nanofluids to enhance thermal performance in closed-loop geothermal wells. And the title, as implies, we're focusing on this exercise on closed-loop systems. The closed-loop systems can be a concentric vertical well or a concentric vertical horizontal well, or a simple U-shape type of arrangement where we have fluid, cold fluid going from one end, hot fluid coming out the other end. And the application of geothermal energy has been talked about quite a bit, about its potential benefits for a low carbon emission energy approach. Now, the reason we are interested in these closed loop systems is because where I come from, we have about 600,000 wells. 300,000 of those are active, 300,000 of those are inactive. If we can harness all that infrastructure and to use it to our advantage to deliver energy, there is possibilities. There are troubles with that. Many of those wells are not in populated areas, so generating heat and transferring heat is not an easy option. Generating electricity could be transferred much further, but the temperatures are low. And so the idea is, if I can increase the temperature at the well output by a few degrees, will that buy me enough oomph to have an organic Rankine cycle implemented for electricity generation? So there are particles that have excellent thermal conductivity, and if we can make nanofluids out of them, we can actually transfer more heat, more enthalpy to the surface than with a single fluid alone. So this part of the presentation was actually taken from Miriam's candidacy exam. And the one thing that every student in the group has to answer is, who cares, right? So this question is essential, because if nobody cares, why are we doing it? So we have a whole bunch of potential possibilities of why should someone care. And also they are asked to say, what is the central question? And in this case, if we have this single nanofluid or hybrid nanofluid, can we actually get extra efficiency from producing well? And so now there is a methodology that most of the students follow. So the first part is the synthesis. I'm not going to talk about the synthesis here. I can see all the Iranian students in the back smiling because they're all doing this as part of their exercises. So, and my Iranians are doing the same thing. And so we have methodology for that. Good. So we synthesize the particles, and then we synthesize the fluids, and then we need to test the fluids for stability. In our case, stability has to be over a period of several months. And then if we do all that, can we incorporate these enhanced fluid properties into some kind of an experiment or some kind of a model that will give us some predictions on the efficiency of the project? That's the purpose of the exercise. So, and this, we don't need to worry about that. We have the definitions. And so, and these are the different methods that we are looking at for evaluating stability, and we use a lot. The reason we use a lot of those is because, first of all, we have to make sure that our results are not dependent on the methodology. And also, if we're going to test at different conditions, whether it's in the laboratory or in the field or in a pilot and so on and so forth, the same methods do not necessarily work at different scales. Plus, I like some toys that I would like them to test. So as an exercise, we start with a very simple thing that we can generate in the lab. And this is a concentric system, about a meter or so long. We can actually do measurements in this in the lab. We can flow some fluids and see if we put some heaters on, what's going to happen, and so on and so forth. And the good thing about that is we can also simulate it in great detail in a multi-physics simulator. What we are using is COMSOL. So we're doing all that. We set up the conditions for the model to match those of the experiment, which experiments, the flowing experiments haven't been done yet. So what we say, okay, we're going to have a steady state, incompressible, Newtonian, and negligible body forces. And what we're interested in, and let's see if I can do that. So we are interested in this. And this is the efficiency improvement coefficient. And it has two terms. One is the heat transfer efficiency compared to a reference fluid. And the other one is the friction, the penalty that we pay because we have something that is more viscous, right? So we have to have a balance of those two. And we want, obviously, this coefficient to be greater than 1. If the coefficient is less than 1, it won't work. So, and so we have equations and more equations. And I won't stay in the equations other than to say that some of the equations that give properties may be empirical, may be experimentally driven, right? Or it may be analytical. We need to evaluate at some point what is the effect of the model performance on these coefficients. So this is part of a sensitivity study that's not part of the discussion today. So what we do is we're looking at, okay, a criterion for stability, and we look as a function of time. So and this is for different mixtures of surfactants with nanoparticles, because we need the surfactant in there to stabilize the suspension. So if the criterion remains more or less horizontal. We're in good shape. The moment that the criterion starts dropping, then we know that we're losing stability. It's time to change the nanofluid. So this will give us the lifetime of the nanofluid within the well under different operating conditions. For these conditions that we played with here, we were able to make sure that these nanofluids remain stable for 100 days. If we can make the 100, 200, bonus, right? If we can keep the 100, let's say, at atmospheric conditions and bring it up to elevated condition and it still remains stable, bonus. But now we have a methodology. And we can have the density ratios, we can have all kinds of other things. I'll show you some more later. Then we do the thermogravimetric analysis and we see how the different components break down as a function of increasing temperature. This is, we use X-ray tomography. So we put the suspension into the X-rays and we're looking at the density distribution of the suspension as a function of height. If the density distribution doesn't change as a function of height, the nanofluid is uniformly suspended. For those of you who are dealing with oil and gas, accumulation of solids in the bottom, right, is settling. We try to avoid that. And this shows very nice uniform composition as a function of height. And each one of these lines corresponds to a different concentration of nanoparticles in the nanofluid. So here we used the thermal conductivity from the literature, and then we can calculate different enhancements for different loads through simulation based on different nanoparticles and different surfactants, right? So we play with all this, we come up with something, and don't worry about anything, just focus. Well, can you focus on the bottom line? I should have put that table upside down, I apologize. So at the bottom line, we have one combination, and we have the same combination at different loads of the nanoparticles, and we can achieve 20% to 40% thermal efficiency improvement. Don't ask me about economics. We're not there yet, right? It's a stepwise procedure. First, let's see if it's feasible, and then let's see if it's practical. It is certainly feasible. So who cares? So we have another guy. Let me see where yes, before we jump to this. So we have another guy who is modeling what's going to happen at surface. And at surface, we would like to take the hot fluid, pass it through an ORC, get the, what electricity we can generate, what is the efficiency of the turbine, and then how much electricity in, let's say, kilowatts we get out per kilowatts putting in. And then there is all this residual heat. And we have to get some use out of it, because if we just put it into the atmosphere, we are heating the environment again, right? So there is thermodynamic efficiency and there is overall process efficiency. So we have to deal with this simultaneously. So the work that this guy has been doing tells us that give me 20 degrees more. Just 20 degrees more. So if we can get this extra 20 degrees through this kind of exercise, bonus. There's other ways. You can say, okay, I'll put a solar panel and I get my extra 20 degrees and so on and so forth. But some of these things may or may not work, thank you very much, to different environments. So this is one of these applications of nanotechnology. So we're going to go to a different application of nanotechnology now. And we are looking at using nanofluid structures as tracers in characterizing hydraulic fracturing. And that can have applications in geothermal and can have applications in tight oil and can have applications in all kinds of other spaces. This was actually an SPE paper recently. So again, who cares? we go in and we do all kinds of fractures. We don't know where the fractures go. We don't know how wide they are. We don't know if they're communicating and so on and so forth. There are commercial tracer products that you can use, dyes, for example. But if you have 30 times 6, 180 fractures, for example, to generate 180 different colors, and then when they mix up on the way back, it's kind of tricky to deal with. So we were asked to look into that for an area I cannot disclose, and we started looking at nanoparticles. And after that, we also started looking at these nanoemulsions. And so there is different types of nanoemulsions that you can use. You can combine those with metal tracers, and if the metal tracers happen to be magnetic, then we can actually use a little magnet and separate the tracer from the rest of the flowing stream, and then we can take it out of the, the stream, salvage it, recycle it, measure it, and so on and so forth. So we have come up with these magnetic Pickering nanoemulsions. Again, there is a whole bunch of steps for the preparation. We try to keep that suspension stable. Same techniques as before. We look at particle size distribution, we look at X-ray, we look at magnetic resonance, and so on and so forth. And what we do is we do experiments. So these experiments can be designed. You can have, for example, something like Professor Cunha's fractured core, and you can flow through that fractured core. Here, we're just flowing through a sandpack, and we hope that the sandpack mimics the propant that is caught between the fractured walls as it's opening and closing. So we can change the load on the sandpack, we can flow the nanoemulsion through, and we can see if it comes out or not. And of course, we inject the nanoemulsion and then we chase it with water. So if all the nanoemulsion comes out, we have zero retention. If all the nanoemulsion doesn't come out, then we have retention, and we have to take that into account. And so, what am I saying? Everyone has seen a CAT scan nowadays. Some of us have been through a few of those, so we know what the technology is all about. This is exactly what we're using in the lab. And what we have is we are monitoring fronts. And in order for us to monitor fronts, we look at something that will absorb X-rays versus something that does not absorb X-rays, and we look at the difference. So as a displacement goes ahead, we have the so-called displacement fronts, and these are different types of experiments with different degree of porosity, for example, different permeability, and so on and so forth. And also it can be different composition of the nanoemulsion. And then what we do is we do the chase. So if we start with something that has, relatively speaking, zero absorption, and we end up with something that has, relatively speaking, zero absorption, then everything that went in came out. No retention, right? So, but if you look at these guys here, especially down here and down here, you can see that there is retention that delays those nanoemulsions to come out. You can fit that in some models that you can calculate mechanical dispersion and so on and so forth. Now, all right, so we have these quote-unquote particles that are moving through the system. Is there a way for us to monitor them? So what we have been doing in the past, for those of you with chemical engineering inclinations, that we used to model a combined CFD-DEM method to model fluidized beds. And so we said, okay, if we take the same application and try to do the nanoparticle modeling, what the hell are we going to get? So don't worry about the equations, look at the model here. So we have a pore structure, and if you take the macroscopic version of the adversant dispersion equation, you will get up with something that looks uniform as you're pushing through that. So can you guys see the particles? So, oops. So if you look in here, there is particles. And these particles are injected at a density, let's say, X particles per cross-section per second, right? And then we monitor how these particles propagate, and we see what we're getting on the other side. And so, and you can play with the injection rate, you can play with all kinds of things. So my boy comes out one day for me and he says, I got negative pressures. So the pressure increases and then drops, and it's something that doesn't make sense. And so it happened to be the day of his candidacy, and we grilled him rather badly, I have to say. So we spent the next 6 months trying to see whether this is a numerical artifact or it's something that is measurable. So he went back and he started doing experiments in a single tube, and he was able to get that there is pressure fluctuations when the particles go through. And then he did an experiment where we had a particle, magnetic particle, and we move the particle inside the fluid, and we have manometers, and we will measure the blips of the manometers, extremely sensitive, and we actually demonstrate that these little pulses actually exist. So good. So now we can feel more comfortable that this is something that is working, and then we can use these models to look at what is the contribution of these nanoparticles to the overall viscosity of the system and how it would fit different empirical equations and so on and so forth. And then we can generate the particle size distribution at the exit, the velocity distribution at different planes, and we can calculate the concentration profiles as a function of time. For those of you who know about mass transfer, concentration profiles as a function of time can be used to get dispersion coefficients. I'm past my time, so I will spare you the last few slides. So close your eyes for a second. There you go. So I want to show this for two reasons. One is because no industry funding, no sponsors, no research funds in Canada. So if you don't have industry support, to get government funding is extremely difficult. So if you look at the energy harvesting processes, I have highlighted the companies which are actually associated with the oil and gas industry that are funding us. And of course, in the unconventional resources, they are all oil and gas companies. I didn't need to highlight them. The people who are not highlighted are developers, electricity distributors, and other non-oil and gas entities which had some money to spare. And there's a few more that, although they promised they had money to spare, they didn't spare them. So with that, I let you ask questions, and thank you very much for your attention.
Thank you, Dr. Kantzas. Questions? There's a comment by one of our board members, Dr. Bob Gochner. Right from the outset, you're talking about, I guess, the water being environmentally safe or something. So he said, don't assume all geothermal fluids, for example, water is environmentally safe or inert. Geothermal fluids can have small but important concentrations of substances that are harmful to humans, for example, arsenic.
That is correct.
So we must be aware and careful. I know this by experience at a geothermal well test outside of Reno, Nevada, where the entire well site crew was hospitalized because of arsenic poisoning. I was fortunate because I was sitting inside a trailer capturing and analyzing pressure data and thus protected. So we've got to be careful.
Luckily for COMSOL, it doesn't have arsenic in it, unless I put it in.
Okay, it's just a comment.
Yeah,
thank you.
It's well taken. It has to be, we have to be really careful. Yeah.
Right, thank you.
Yes.
Thank you, Professor. I had a quick question about the first project, nanofluids for AGS. Not as much about the economics, but about the scope, since, as you probably know, in AGS, the main concern is that we're imposing such thermal loads in these wellbores that the near wellbore region is going to be cooled off quite fast. So whoever has done simulations on this, you know, that even if you use dozens of laterals, you find a thermal breakthrough around your producers, no? And then if you're increasing the specific heat capacity of the fluids, this is not really going to, you know, like enhance the performance of such a system. So I was wondering if you see another application for these nanofluids, whether this is in geothermal industry or somewhere else, or if you have a word about the scope.
Right. So for this specific project, the student was asked to look at the closed system, and we have a parallel detailed COMSOL model that will show us what you mentioned about the temperature profiles. The objective of the project was to see whether these efficiency coefficients can actually be generated and modeled accurately, and whether we can use these efficiency coefficients to scale up. Okay? And so we did not look at external adverse effects yet, but the models are capable of looking at that. So the other thing that is important for you to, not for everybody to understand, is that it's not like a Reynolds number that you can just adjust. You say, at the lab I have this Reynolds number, if I do the same Reynolds number at the field, I'm good. Because these fluid properties change with temperature and pressure, it doesn't mean that the efficiency coefficient that we look at surface is the same with the efficiency coefficient at the 2 kilometers or the 3 kilometers, right? So that's a first objective before we look at some of the other stuff. Okay.
Okay. A question, yes, from Dr. Iraj Vershagi from the University of Southern California, a great mentor of one of our chairs, Dr. Benham Jafarpour. He asked a question about what do you think would be the impact of development of geothermal energy on energy supplies outside of the USA?
So my focus is Canada. I cannot talk about other countries at this point in time. My focus is in Canada, and in Canada, we have identified only one spot near populated areas that we can actually do full-scale traditional geothermal energy for electricity. And that's called the Mount Meagher, and it's northeast of Vancouver. If you look at the province of Alberta, the highest temperature point that we have is 130 C. There is one company that has actually claimed that they generate economical electricity out of that. The rest of the companies are either focusing on heat or looking for funds to do fancy things. Some of these fancy things is to drill below basement. So there are groups that advocate that we should go, 6, 7, 8 kilometers down and see what we're going to find. And then there are some other people who look at this as technology development for export. But for the province of Alberta, as it stands today with the technology of today, most of these applications will be for heating, agricultural applications, small community heating, and a lot less in electricity generation.
Okay, thank you. It's time to close out this talk here. Thanks again, Dr. Kantzas.
Thank you.